So this is our final video for the forces unit, and we're going to look at solving friction problems. So we're going to kind of combine everything from chapter 4, some stuff from chapter 3, and also heading back to some kinematics and those 5 key equations. So we're going to do 3. So here's our first one. And this is an example of static friction acting on 2 or more objects. So remember, static friction means that we are not causing any motion. So here we've got 2 sleds tied together with a rope, and we have a coefficient of static friction between each sled and the snow is, and we know that that's 0.22. So let's go ahead and write down what we know. Because if we're given that coefficient of static friction, we're probably going to have to calculate our force of static friction. Okay, so we have a child with a mass of 25 is on sled 1, and a child with a mass of 34 is on sled 2. So let's just draw kind of like a little picture of what's going on. So this is going to be sled 1, sled 2. So we've got 25 kilograms and we have 34 kilograms. So if we think about this, and we're trying to figure out what the greatest horizontal force the adult pulling the sled. So here's our adult who's pulling the sleds, can exert without moving the sleds. So if we're trying to figure out the maximum force, that means we're looking for the mass of all of these things. So we want to combine our masses. So like I said, when you're given your coefficient of static friction, you're probably going to have to calculate your force of static friction, because it's the only formula on your formula sheet that has the coefficient of static friction. So, and in order to calculate the force of static friction, you know you're going to have to use your normal force. So really, the trickiest part here is figuring out that you want to use your total mass. So 34 plus 25 is 59 kilograms. So when we go to calculate our normal force, we want to use 59 times 9.8. So we get a normal force of 578.2 newtons. Okay, so then we could go ahead and figure out our force of static friction. And since we've already rearranged that formula, I'm just going to put it in here. Okay, and then we can go ahead and continue solving. So our force of static friction then is 127.2 newtons, which we would round to 130 so that we only have our 2 significant digits. But what that means is that that's kind of our force of static friction, and it's also going to be our force of tension, okay, if we were talking about both sleds, because we're not moving. So let's go ahead and look at part B. And part B is asking us to calculate the magnitude of the tension force between the sleds. So between the sleds means that we are only worried about the mass that's behind the rope. So in this case, we're just worried about sled 2, which is our 34 kilograms. And so our backwards force is going to be our force of static friction, and our forward force is going to be our force of tension. So let's write an F net equation. So we're going to do Ft minus the force of static friction. And because these sleds are not moving, that means our F net is equal to 0. And then we can move our force of static friction over to the other side. So our force of static friction is equal to our tension force. So really what we need to do now is we need to calculate our new force of static friction, because now we only care about the 34 kilograms. So that means our normal force is changed. So let's go ahead and calculate that new normal force. So there's our normal force. And then we could go ahead and calculate our force of static friction by multiplying those together. And so our coefficient is still the same. So we get 73.3 newtons, which we'd round to 73 newtons because we just want two significant figures. So again, our force of tension is equal to our force of static friction because our F net is going to be 0 because we don't have any motion. All right, so while static friction is talking only about things that aren't moving, static friction can cause motion, and that's what we're looking at in this example. So here we're told that we have a coefficient of static friction between a runner's shoe and the ground, and that value is 0.70. And it's asking us to determine the maximum acceleration, okay? And we have a mass. And she's starting from rest, which isn't really a huge deal for us right now. But if you don't really get this, what I want you to do is I want you to get up and walk around and focus on what the shoe that is making contact with the ground is doing. So if you can imagine, you're taking a step forward with your right foot. So your right foot is the one that's in motion. If you're looking at your left foot is not moving. And so that is static friction. And because you have that kind of traction with the ground, you can push yourself forward. So what we can do is we can draw our free body diagram that represents this situation. So it's like that. So the only forward force we have is that force of static friction because you're pushing back on your shoe and you go forward. So really it's another example of Newton's third law of motion. So let's go ahead and calculate our normal force. Sorry, so when you do 57 times 9.8, you get 558.6 newtons. So that's our normal force. So we're going to go ahead and calculate our force of static friction by doing our coefficient of static friction times our normal force. So we get 391.02, so 391 newtons. So now if we go back up to our equation here, we can write an F net equation, and it's showing you that it's equal to our force of static friction. So if F net is equal to our force of static friction, that means we can replace this with mass times acceleration, and we can put our force of static friction in, and then if we divide both sides by our mass, we will get our acceleration. So we get 6.9 meters per second squared. And you can put your direction. It's not really given to you in the question, but you can always imply that motion is in the forward direction unless you're told otherwise. Okay, so again, that's an example where we're using force of static friction, but you are actually moving. It's causing you to move forward, but the shoe that is in contact with the ground isn't moving, and so that's why it's a static friction question. So it can be kind of hard to rationalize there in your brain. So here's an example where we've got kinetic friction and it's causing motion. So we have a 300 kilogram box that's sliding across a level floor, and we have our coefficient of kinetic friction is 25. So automatically you should recognize that you're probably going to have to calculate your force of kinetic friction, which means you're going to need a normal force. So what I'd like to see you guys try and start doing is write down what you know and calculate what you can, and then it allows you to get some part marks here and there. All right, so once you've got a mass, you could go ahead and you could figure that out. And then, so we have a V1 here of 1.5 meters per second, and it's left. And they apply a horizontal force, so that's going to be an applied force. of 150 newtons right to stop the box. So that means our V2 is 0 meters per second. Okay, how far does it travel? So that means we're trying to figure out our D. So just like when we were doing our chapter 3 questions, if we're asked to figure out our displacement and all we're given are a bunch of forces, that means first we need to figure out our acceleration. And if we need to figure out our acceleration, we need to draw a free body diagram and write an F net equation. So here's our box. It has a normal force. It has a force due to gravity. It has an applied force. And here's what I'm going to do. I'm going to change colors here for a second, and I'm going to draw in your direction of motion. So your direction of motion is that 1.5 meters per second towards the left. And why that's important is because that means our force of friction is actually forwards, because friction always acts opposite to the motion. Okay, so that's a little bit tricky. We are moving to the left, which means kinetic friction is acting to the right. So let's go ahead and write an F net equation. So we're actually going to be adding our applied force and our force of kinetic friction. Okay, so we haven't calculated our kinetic. So let's go and calculate that. So we're going to do our force, our coefficient of kinetic friction times our normal force. So we're going to do 0.25 times 2940. So we get 735 newtons. So our F net then is equal to our applied force, and we're told in the question that that's 150 newtons, and we're going to add our 735 newtons. So we get 885 newtons, and then we know we can replace F net with MA, divide both sides by our mass. So if we do that, we get 2.95 meters per second squared. So it's asking us to figure out our displacement, and so we have our V2, we have our V1, we have our acceleration, and we're being asked to figure out our displacement. So we're going to go ahead and use that equation. So let's rearrange it. Okay, and let's go ahead and put our information in. And when you do all of that math on your calculator, you get 0.38 meters. So then we need to assign a direction to that. So the box is sliding to the left, so that means our displacement is to the left because it has to go in the direction of our motion. So that's the end of that question. So again, we had to use the information in the question to figure out our force of kinetic friction. We had to realize that the force of kinetic friction was acting in the same direction as the applied force because friction always opposes motion. Then we wrote an F net equation, which allowed us to solve for acceleration. And then we subbed it back into one of those 5 key equations from our very first unit, and we were able to solve for our displacement.